Good morning. My name is Huanghai Lam, and today I will present my final year project, OpenLane RISC-V design, from RISC-V CPU architecture design to the open source ASIC implementation. And this project will explore the complete flow from processor architecture design in Verilog to open source ASIC backend implementation and final GDS generation. The motivation for this project comes from the growing accessibility of open source ASIC design tools. First, the open source EDA tools now make the ASIC design more accessible for learning and research. And second, RISC-V is an open ISA. ISAs stand for Instruction Set Architecture, and it makes it very suitable for the academic purpose because it's open source and totally free. And third, the combination of the OpenLane ASIC flow plus the Skywater 130 Open PDK, the process development kit. It enables a complete RTL to GDS flow without any commercial tools. So based on this, the project objectives were to implement a functional RISC-V CPU in Verilog, and I choose the instruction set using the R32I, which is the integer-based 32-bit instruction for RISC-V. And to compare the trade-offs across multiple architecture versions, and also to verify execution through simulation and core mark benchmarking, and to complete the backend physical design using the OpenLane flow and inspect the final layout. So the project goal is not only to build a CPU, but also to demonstrate a full open source digital IC design flow. This project follow a 6-step methodology. And first, I would define the architecture and choosing the ISA first. And for my design, I choose the R32I, just like I mentioned. And then I will implement the RTL, writing the Verilog modules and the corresponding test benches. And I will verify the design using simulation with the verilator and check the waveform using GTK wave. Fourth, I prepare the core mark benchmark and build it into hex file for simulation to do the benchmarking to compare the performance. And finally, I will run the OpenLane backend flow, including the synthesis, floor planning, placement, block tree synthesis, routing, and sign-off, and to generate the final GDS file. And I open it using a KDL and GDS 3D to inspect the file. And for my final year project, my CPU architecture evolved across 3 major versions. So the first version was a single cycle core, which is a functional baseline, and it only for simulation only. And the second version is the multi-cycle non-pipeline CPU, and it is also the first version of backend feasible design. And the final version was a 5-stage pipeline plus a dynamic branch prediction core, and the frequency is the highest, and it has better throughput. So the project progressed from basic correctness to timing feasibility and finally to higher throughput. And the project aim is to develop a higher performance CPU. And the project aim is to develop a high performance CPU. So let me talk about the first version. The first version is a single cycle R32I CPU. And in this design, every instruction completes in 1 clock cycle. And this version was mainly used as the initial RTL reference for the functional verification and ISA validation. Its advantage is simplicity because the data path and control are straightforward. It is easier to debug and confirm the instruction behavior in the simulation before moving to the more advanced microarchitecture. However, the major limitation is that it assumes the zero latency memory. So it is not really practical in real life implementation. It is not practical for real ASIC implementation. So I designed for a version 2, the multi-cycle non-pipeline CPU. And to solve the timing issue, I redesigned the CPU into a multi-cycle non-pipeline architecture to fit the 1-cycle SRAM. And in this version, the instruction execution was divided across multiple clock cycles. and this made the design compatible to the real memory. And this was the first version to achieve both functional verification and successfully pass the OpenLane flow. And you can see that the majority difference in this architecture diagram compared to the single cycle one is this version. It has more registers in the fetch stage. It has some registers in the fetch stage to match with the latency with this instruction memory, the synchronous instruction memory. And to further achieve a higher frequency and also a higher performance, I improved the microarchitecture to a 5-stage pipeline version. And the 5-stage pipeline, they are instruction fetch, instruction decode, execution, memory, and also write back. And you can see in this architectural diagram, there are 4 pipeline registers. So it is a 5-stage pipeline, and this improved the throughput and frequency scalability. But benchmarking revealed a new limitation because the pipeline core is suffer from the control hazard, especially from the branch instructions, which reduce the core mark per megahertz result. And for this design, the branch flushing penalty is around 2 cycles. So that motivated the addition of the dynamic branch prediction. And for this branch predictor, it contains 2 parts. One is the branch history table, which predicts the taken or not taken using a 2-bit saturating counter. And the purpose of this BHT is to predict the direction of that branch. And the BTB, branch target buffer, stores to predict the target PC for recently seen taken branches. And the main purpose of this BTB is to predict the address of the corresponding branch. So how they work, during the instruction fetch, the CPU checks both the BHT and the BTB. If a branch is predicted taken and it matches with the BTB hits, the PC will be redirected immediately to the predicted target. So if the prediction is if the prediction is incorrect, the pipeline will be flushed and the PC will be corrected in the execution stage. So with this mechanism, the core mark per megahertz improved from 0.83 to 1.02, which increased around 23%. However, the trade-off is additional area and power, but it reduced the control hazard penalty and makes the predictor worthwhile. And this is my core mark benchmark demonstration, and I prepare a YouTube video. And first, I will build the core mark from C program into a machine code, and I'm using Makefile and also the GCC RISC-V GCC toolchain to build it into machine code. And I copy the machine code, the hex file, to my working directory. And then I will run it in later, and you can see that it is running. The benchmarking is running. And let me skip it to the end of the simulation. So at the end of the simulation, you can see that there is a result of my core mark benchmark. And after the RTL verification and benchmarking, I ran the design through the OpenLane backend flow, and I write my own configuration file and also the corresponding constraints for this OpenLane backend implementation. And the completed stage include the RTL synthesis, floor planning, placement, clock tree synthesis, routing, and also sign-off checks. So this project is not limited to front-end processor design. It also includes a complete physical implementation flow using the open source tools. And this is the manufacturability report. And you can see that for all of the checks, there's no violations. The design rechecking and layout versus schematic, and also the antenna violations, they're all 0. They're all clean. So if I update my design, and this is the GDS layout that I opened using the KLayout open source tools. And this is the 3D view, which I use the GDS 3D, another open source tools built by another PhD team. And for this top view graph, you can see that there's a blue area in here. This blue area is actually my CPU core. And for these two blocks, they are the SRAM cell. They are the SRAM macro, the memory. And I use 1 KB memory for this design. And this is the other side of the 3D view. And also, this slide summarize the PPA comparison across the implementation versions. PPA stands for power, performance, and area. So the single cycle version is included only for benchmarking comparison because it was simulation only and did not complete the backend implementation. And among the all the versions, the multi-cycle CPU achieved the lowest area and power. And the 5-stage pipeline one reaches the highest frequency at 100 megahertz. But the core mark per megahertz was lower due to the branch hazards. And after adding the dynamic branch prediction, the DBP, the benchmark efficiency improved to 1.02. Although this came with increased area and power, but for this power, it is still a relatively low power for a CPU design. So this slide highlights the central trade-off of the project, and simpler design some more area efficient and power efficient. However, it is low performance, and with a more advanced design, it improves performance with additional hardware cost, additional power, and also additional area. And to give additional context, this slide compares my result with several published RISC-V calls. The purpose of this slide is not to claim a perfectly fair apples-to-apples comparison, because the designs differ in different ISA. Instead, this slide gives a rough external positioning of the proposed design. And my design achieved a 1.02 core mark per megahertz, which is higher than the Neo RV32 small, and slightly higher than the performance version of the Neo RV32. However, it's still below more performance-oriented designs, even though the Hummingbird E203 is only a 2-stage pipeline. The one reason behind that is that my design is based on the RV32i only. Without the M extension set, the M stands for multiplication. It is a hardware multiplication. And for my design, there are no hardware multiplication. And so the efficiency of the core mark per megahertz will be lower than those with the so the core mark per megahertz efficiency will be lower compared with other versions with the M extension. And you can see that even for the same Neo RV32, the one with the M extension have a near triple performance than the original one. During the project, several engineering challenges has to be solved. At first, there were antenna violations. It occurred during the routing, and which were fixed using the heuristic dial insertion, which is using the OpenLane flows its own default algorithm to do the dial insertion. And the second is the single cycle SRAM timing mismatch and make the original architecture unsuitable for real backend implementation. And this led to multi-cycle redesign. And third, the pipeline core has low core mark per megahertz because of branch hazards. So I add the 2-bit BHD plus a BTP branch predictor. And fourth, the SRAM macro placement initially caused a congestion. The default setting is not enough. So I fixed it with a manual macro placement using the by manually writing the placement configuration file. And finally, the early stalling logic create a critical path issue when I'm doing the front end design. And And this was resolved by stalling only the pipeline registers, while instead of the PC and the instruction fetch path. And overall, this challenge is to show that the real processor design is not only about RTL correctness, but also about the interaction between architecture, timing, and physical design. And this is my future work. There are several limitations for my design. First is the for my design now, it doesn't have the external memory access bus. So in future work, I decided to add a bus interface to add an AXI or wishbone bus for external memory access, because the on-chip memory is actually very expensive and it costs really much area. So I need the external memory access to access the uh, to access memory outside of the chip. And I also would like to make it extended it to a full SoC by adding the UARTs and other peripherals. And for the architecture extensions, I would like to add the instruction and data cache after I implement the bus interface. And also I will add the M extension to strengthen the performance of my CPU design. And the final goal is to implement a out-of-order execution design and or the multi-threading design to explore the more higher performance and more modern design. And this is my conclusion. So to conclude, for my design, this project implements three architectures, CPU, the single cycle, multi-cycle, and 5-stage pipeline, and they are all in RP32 ISA. And this processor also successfully executed a call mark, which validating the full front-end flow, and also do the comparison of the several designs. And the backend flow was completed in OpenLane, and the final GDS was generated and inspected in KLayout and GDS3D. And in addition, dynamic branch prediction improved the pipeline core, which is about 20-30% improvement for the benchmarking. And overall, this project demonstrates a complete open source CPU to open source RTL to GDS2 design flow, and from architecture trade-off analysis to physical implementation. And that's the end of my presentation. Thank you.